At an elevation of nearly 1,900 meters in the Swiss Alps, there is a place that only a few months earlier was a calm blue mountain reservoir, but soon after can turn into a massive frozen block, isolated by a long winter. It was here that Swiss engineers made a bold decision to build an entirely new dam directly in front of the existing Spitallamm Dam, which is still in operation. This decision was not made to replace a structure that had already failed, but to prevent a hidden risk that was slowly developing inside the body of the dam. To make that possible, they had to lower the level of an entire high-altitude reservoir, drill through solid granite rock, and gradually redirect the full water flow into a completely new structure, right in the middle of one of the harshest construction environments in Europe. Grimsel Reservoir sits at the center of one of Switzerland's most important pump storage hydropower systems, where water is stored at an elevation close to 2,000 meters, so it can be used to generate electricity during periods of peak demand across the national grid. In a system like this, each dam is not just a standalone water barrier. It is a critical link that directly affects the stability of the entire energy network behind it. The original Spitallamm Dam was built in the early 20th century, at a time when dam design standards were very different from today. After decades of operation under high water pressure, seasonal temperature swings, and the harsh conditions of a high mountain environment, engineers began detecting cracks forming inside the concrete structure. These were not signs of an immediate failure, but they were serious enough to raise an important question. Could the dam still meet modern safety standards for the decades ahead? As a result, Switzerland decided to construct a new Spitallamm Dam directly in front of the existing structure, allowing the entire system to be gradually transferred to a safer and more reliable configuration for the future. For several months, the water level of Grimsel Reservoir was gradually lowered meter by meter. What had once been a cold blue alpine lake at the center of the Swiss Alps slowly revealed a wide stretch of exposed granite bedrock in front of the Spitallamm Dam, an area that had previously remained completely underwater. Once the rock foundation at the bottom of the reservoir was fully exposed, construction teams were finally able to directly access the future foundation line of the new dam. But for a structure designed to withstand enormous water pressure like Spitallamm, simply exposing the foundation surface was not enough to begin placing concrete. Engineers first had to go deeper, into the granite mass inside the mountain itself. A network of technical tunnels was drilled into the mountain surrounding Grimsel Reservoir to reach the future foundation zone from below and from the sides. Under the extremely hard granite conditions of the Alps, these tunnels could not be excavated using ordinary methods. Instead, each section was advanced through a repeated sequence of drilling, blasting, clearing, and reinforcement, carried out with high precision to maintain geological stability around the construction zone. Immediately after each tunnel section was opened, the tunnel walls were stabilized using shotcrete and reinforced with steel rock bolts anchored deep into the bedrock. These reinforcements helped maintain tunnel stability throughout construction and created underground working corridors that allowed engineering teams to move forward with the next critical stage of foundation treatment. Although the granite bedrock at Grimsel is naturally very stable, engineers still had to address a risk that cannot be seen with the naked eye. Natural fractures inside the rock mass could become potential seepage paths beneath the dam in the future. Once the reservoir returns to operation, the enormous water pressure behind the new dam could force water through these tiny cracks if they were not treated in advance. For that reason, along the entire alignment of the future dam, a dense network of deep boreholes was drilled beneath the foundation. Cement grout was then injected into these holes under high pressure to seal microscopic voids within the granite structure. The resulting grout curtain acts as an underground seepage barrier beneath the dam foundation, almost invisible from the outside, but essential to the long-term watertight performance of the entire structure. The next phase of the Spitallamm replacement project involved building a hydraulic tunnel system that would allow engineers to control water flow throughout the process of replacing the existing dam. The two most critical components of this stage were the connection tunnel and the bottom outlet tunnel. The connection tunnel functioned as an intermediate hydraulic corridor, maintaining continuity between Grimsel Reservoir and the new regulating structure of the future Spitallamm Dam. This tunnel allowed engineers to gradually control the movement and direction of water according to construction progress without interrupting the operation of the hydropower system downstream. In a replacement dam project built directly in front of a reservoir that remained in operation, maintaining this level of hydraulic connectivity was essential for allowing the construction site to expand safely, step by step. At the same time, the bottom outlet tunnel was constructed as a low-level outlet designed to withstand the direct water pressure from the reservoir behind the dam. It became one of the most critical load-bearing components of the hydraulic tunnel system, because it allowed engineers to regulate reservoir water levels throughout the construction phase and continued to serve as a key control structure after the new dam entered operation. Since the tunnel must operate under high water pressure for long periods of time, its geometry, structural concrete lining, and the placement of regulating equipment were all controlled with extremely high precision from the earliest excavation stages. Inside these tunnels, the construction space quickly developed into a complex underground engineering system. After each tunnel section was excavated, using a controlled drilling and blasting sequence through the dense granite of the Alps, exposed rock surfaces were stabilized with shotcrete before the installation of a long-term pressure-resistant concrete lining. Along the tunnel walls, pressure pipelines, grouting lines, anchoring systems, and control equipment were installed progressively during each construction stage, forming a complete underground flow regulation network embedded deep inside the mountain. From the outside, the Spitallamm construction site now began to change noticeably. The deep excavation work inside the mountain gradually gave way to a new phase, organizing large-scale material production in preparation for building the new dam body directly in front of the existing structure. At an elevation of nearly 1,900 meters in the Swiss Alps, concrete production was no longer a simple logistical task. Unlike hydropower projects in lower regions, the Grimsel site is located far from major supply centers, while the available construction season each year is strictly limited by harsh high mountain weather conditions. As a result, transporting concrete from outside the region was almost impossible at the scale required for a replacement dam. At the site, every material component, coarse aggregates, sand, cement, and water, was carefully controlled using mixed designs adapted specifically for alpine construction conditions. In massive concrete structures such as the new Spitallamm Dam, the cement hydration process generates significant internal heat within the concrete. If not carefully managed, temperature differences between the core and the surface could create internal stresses even during the early stages of curing. For that reason, concrete control at Grimsel did not stop at the mixing stage. The temperature of the mixing water, the moisture content of the aggregates, and the transport time after mixing all had to be precisely adjusted according to the actual environmental conditions at the construction site. At the same time, internal concrete transport routes were organized as part of the overall dam construction workflow. Transport distances were minimized as much as possible to ensure that fresh concrete could reach the placement area in a stable condition before the setting process began. This was especially important for the large concrete blocks forming the new dam body, where each placement layer had to maintain a high level of uniformity to ensure the long-term performance of the structure. Another major challenge came from the seasonal construction rhythm of the Alps themselves. Unlike hydropower projects in lower elevations that can maintain progress year-round, outdoor concrete works at Grimsel could only be carried out during relatively short periods of favorable weather between two long winters. This forced the entire on-site material production system to operate with a very high level of precision in order to make the most efficient use of each construction season. Thanks to the establishment of a dedicated concrete production system at nearly 1,900 meters above sea level, the new Spitallamm project was able to maintain steady progress on the construction of the new dam body in front of the existing structure, preparing for what would become the most technically sensitive stage of the entire replacement dam project. As the concrete layers of the new dam body in front of Grimsel Reservoir gradually reached the elevation required to take over flow regulation functions, the Spitallamm replacement project entered a decisive phase, establishing a direct hydraulic connection with the existing dam located behind it. Unlike many hydropower projects that can divert water early in construction using independent diversion tunnels, the transition at Spitallamm had to take place while Grimsel Reservoir continued operating under normal conditions. This meant engineers had to drill directly through the existing dam structure according to a carefully controlled technical sequence, allowing regulation functions to be transferred step by step to the new replacement dam in front. This drilling process required not only extremely high geometric precision, but also careful control of hydraulic balance throughout the entire reservoir system. Thanks to the regulating tunnels previously constructed inside the surrounding mountain, water flow could be redirected gradually without interrupting the operation of the hydropower plant downstream. Once the hydraulic connection was successfully established, the next step was the installation of a system of high-pressure steel gates, mechanical components that play a direct role in controlling water discharge during the long-term operation of the new dam. Unlike the large concrete blocks used to build the dam body layer by layer, these steel gates are precision mechanical systems designed to operate reliably under extremely high water pressure behind the reservoir. For that reason, the installation position, structural geometry, and opening and closing performance of each gate had to be calibrated with very tight tolerances before entering the testing phase. When the steel gate system began operating in coordination with the regulating tunnels completed earlier, the replacement dam in front of Grimsel Reservoir officially took over the primary flow control role from the older structure behind it. This marked the most important transition point of the entire replacement dam project, the moment when the new dam was no longer just a parallel construction structure, but became the central regulating element of the entire Grimsel Reservoir system. At Grimsel, the construction site itself was already part of the engineering challenge. The project is located at nearly 1,900 meters above sea level in the Swiss Alps, where construction conditions are not determined by schedule alone, but by the weather. During many winter months, deep snow and freezing temperatures forced most outdoor work to stop completely. As a result, each construction season became a short but critical window that strongly influenced the progress of the entire project. The mountainous terrain also created major logistical challenges. Unlike construction sites located near cities or major transportation networks, most materials, equipment, and heavy machinery for the Spitallamm project had to be transported along narrow alpine roads leading up to Grimsel Reservoir. Because of this, construction progress depended not only on on-site engineering capacity, but also on the ability to organize deliveries precisely during the limited construction season each year. Under these conditions, the role of the workforce became especially important. Working in an alpine environment requires more than standard construction skills. It also demands the ability to adapt to low temperatures, steep terrain, and restricted working spaces. From teams operating the on-site concrete batching facilities to tunnel crews working deep inside the mountain and technicians installing hydraulic regulation equipment, every activity had to be carefully coordinated to make full use of each favorable construction period during the year. Another major challenge was that the entire Spitallamm construction site was not built on an empty location. The new dam was constructed directly in front of an existing structure that continued storing water and operating at the same time. This meant engineers and workers had to carry out construction activities in an environment where every technical intervention had to be carefully controlled to maintain the stability of the reservoir system throughout the process. It was this combination of high-altitude terrain, seasonal weather limitations, and parallel operation alongside an active dam that made Spitallamm one of the most complex replacement dam construction sites within Switzerland's hydropower system. In the heart of the Swiss Alps, where weather conditions can slow construction for months each year and the terrain makes transportation far more complex than at typical construction sites, a new dam is gradually taking over the role of the structure that has controlled Lake Grimsel for decades. The Spitallamm replacement dam is not simply a hydropower infrastructure upgrade. It is a carefully managed engineering transition carried out while the existing system behind it continues to store water, generate electricity, and operate as usual. From lowering the reservoir level to open a construction site on the lakebed, excavating deep tunnels inside the mountain to prepare a new hydraulic regulation system, organizing concrete production at nearly 2,000 meters above sea level under harsh alpine conditions, to eventually drilling through the existing dam to transfer the regulation function completely to the new structure in front. Each stage must be executed in an almost perfectly controlled sequence, where even small errors could create major risks for the entire system. Projects like Spitallamm reveal a reality that is rarely seen. Many of the world's most important infrastructure systems are not built under convenient conditions, but in places that are among the most difficult to access, the coldest, and the most complex in terms of terrain. And if you would like to continue exploring how massive infrastructure projects are built in extreme environments like the Alps, across the open ocean, in deserts, or deep beneath centuries-old cities, don't forget to follow Mandarin Tech, where we look behind structures that may seem familiar to understand how they are actually built.